Welcome to the recital for Module 3. This week, we focus on understanding the relationship between causes and consequences in order to be able to quantify the consequence of our possible future actions. Our main focus will be to try to understand, like you did in class, what drives our credit score. Let's get started in R. You're not familiar with RStudio, and the first thing you do is to set your directory to the folder where you have downloaded the credit scoring dataset. To make sure that the memory of our current R session is clean, we run the following line. We then load our dataset. By now, you should be familiar with the sep and header arguments, but if you do not remember what they are used for, remember that you can always type the name of a function in the command line preceded by a question mark in order to have access to its documentation, which includes a description of its arguments. Here, we would type question mark read.table and hit enter. Let's now have a look at our variables with the str function and see some summary statistics with the summary function. The str function outputs a description of our variables. We find out that we have 300 observations and 10 variables in this dataset. First, we have the income variable, which represents the income in thousands of US dollars. We then have the rating variable, which represents a credit score. Then the cards variable, which is the number of credit cards that the user owns. Then the age variable represents the age of the individual. The education variable shows the number of years of education of the individual. The gender is a factor that says male if the individual is a male, or female if the individual is a female. The student variable is again a factor and tells us whether or not the individual is a student. The married variable tells us whether or not the individual is married. The ethnicity variable provides us with the ethnicity of the individual, for example, African American, Asian, Caucasian, etc. And the last variable is the balance, which corresponds to the average credit card debt for the individual. To have a better understanding of our data and have in mind the order of magnitude of our variables, we run the summary function on our dataset. We can see, for instance, that the minimum income value is $10,350,000. The maximum is $186,633,000, while the mean value is $44,005,000. Similarly, the rating variable has a minimum value of 93, a maximum value of 949, and a mean value of 348.1. This gives us a good idea of the order of magnitude of the rating variable. In this dataset, our dependent variable is the rating variable. Or in other words, it is the variable we want to predict based on our other variables. Before we move on to any kind of prediction making and modeling, we would like to know how our rating variable is distributed in our dataset. A histogram is a great graphical representation of the distribution of a numerical variable. To build a histogram in R, you use the hist function and you pass on as an argument the numerical variable that you want to explore. If we run this line, we get the histogram that you can see on the bottom right corner of my screen. Let's explain the output quickly. We see the frequency on the vertical axis and the rating variable on the horizontal axis. What the code has done is to define buckets which contain credit scores between 0 and 100, between 100 and 200, between 200 and 300, etc. until the last bucket, which contains credit scores between 900 and 1000. What do we see visually? Well, we see that the distribution is skewed to the right. That means that while most our values seem to be between 100 and about 400, we have credit scores way beyond, up to our last buckets. Now, what we're trying to do is to understand the main drivers of the credit score. One thing we can do is to have a look at the correlations between our variables. As explained in class, it only makes sense to do so with numerical variables. To obtain the correlations of our variable in R, we use the core function that you can see here and pass it on as arguments our datasets, so data, excluding the categorical variables, which are, if you remember, gender, student, married, and ethnicity. If you look at our dataset, these categorical variables are in the 6th to the 9th column, so we only select column 1 to 5 and column 10 of our dataset by using the combine or C function. As explained in class, the output of the correlation function provides us with numbers that do not really tell us which variables are most important or significant in predicting the credit score. We do not know either how they contribute to that score. Is it positively or negatively, for instance? So as you did in class, we'll use a regression and learn how to create a regression model in R. To create a linear regression model in R, we use the LM function. Our first argument is the values we input to build a model. So the rating variable comes first as it is the variable we're trying to predict. Then you insert a tilde, and to tell R that we want to use all the other variables, we insert a dot. Note that if you wanted to use only some of the variables to build your model, you would write the name of those variables and separate each of them by a plus sign. Our second argument is to set data equal to the datasets that contains our variables. Here, our dataset is called data, so we set data equal to data. Now that we have a model, we should find out how it performs. As in class, we'll stick with in-simple accuracy. Note that a more rigorous approach would be to test the model on data it has never seen before. Just to be clear, in-simple data is the data we use to build a model. In our case, it is our dataset. For each of our observations, the model estimates the value of the credit score based on the other variables, and these are called the fitted values. To assess the model on in-sample data, you can use correlation between the actual values and the fitted values, which you can obtain by calling the correlation function. As you can see, we obtain 0.90, almost 0.99 as a correlation coefficient. But as explained in class, correlation has some limitation. To circumvent these limits, we can use a more intuitive and visual approach and plot the fitted values as a function of the actual values. Let's run the line. We can clearly see that the model does pretty well. That said, it does not do as good of a job on the lower values. In fact, it seems to be pretty off for the lower values. Once we're confident in our model, the next thing we can do is to check out the output of our regression model. To do so in R, use a summary function on your model like this. You learned in class how to quickly interpret the results of a linear regression, but let's go very quickly over some of our main takeaways here. First, the star system in R tells us that the statistically significant variables are the income variable, the student variable, and the balance variable. Because the absolute value of the t-value of the balance variable is the largest, we conclude that it's the strongest driver, then the income, and then whether or not the applicant is a student. Finally, we want to know whether the impact on the rating is positive or negative for each predictor. We can find that information in the estimate column. Unsurprisingly, a negative coefficient indicates a negative impact, while a positive coefficient indicates a positive impact. So here, the fact that the applicant is a student impacts negatively on the score. In other words, it lowers the score. On the other hand, the positive coefficient next to the balance indicates that the higher the balance, the higher the credit score. Same for the income, which is pretty intuitive. Now, if we wanted to show our technical findings to a business audience, we could plot the rating as a function of the balance and show that the slope is positive and that indeed, the higher the balance, the higher the rating. If we quickly run the same line with the income instead of balance, we can also see visually that the higher the income, the higher the rating. That's it for this example. I hope this made things clear for you, and I will see you in the next video.